So in this section, we're going to dive deep into how embedding models are formed, the different types of embedding models, and even how they are trained. And so embedding models are commonly trained from a base encoder only model. And from what I researched, this is consistent across modalities: image, audio, and text. And so what do I mean by a base encoder only model? So if you see over here, this is your vanilla transformer that came out in 2017, and on the right side right here of this transformer model, you have the decoder portion. On the left hand side right here, you have the encoder portion. Now this encoder portion is primarily where most of the current embedding models that we see today are based off of. They only train this part right here. Now, some of the most common variations on this encoder only model here are BERT, which BERT literally was this encoder model with nothing changed. DistilBERT, Roberta, and XLM Roberta. These are the most common base models, and most of the models that you see are just going to be variations or slight changes to this encoder only model. And so these embedding models are trained via loss functions that will bring similar points, similar embeddings closer, and then those that are dissimilar further apart. And that's from the most simplest explanation that I can give is that they give you two pieces of, let's say, two sentences that are semantically similar, and we want the embeddings produced by the model on both of those sentences to be pretty close in space, right? And for sentences that are dissimilar, we want those embeddings to be as far apart as possible. And so when you train a model on many different pairs like that, what are called positive and negative pairs respectively, you finally get a model that's able to compare and contrast text. And in order to do that, it's had to encode a lot of meaning around the text that it was trained on. So we're actually going to step now into some code, walk through a notebook, and show you how embedding models work under the hood. So I have 3 embedding models here that I pulled from Hugging Face. We'll get into how I came to select these when we look at the Hugging Face text embedding leaderboard. But I'm just going to load them all in, and I'm going to look at their individual structures. So you can print out the model here. I'm loading it in here, and then I'm printing out the model here. And as you can see, so for our first one, that's the int float multilingual E5 large instruct, the transformer portion itself is an XLM Roberta model, which is one of the models that we talked about. And then you can also see that it does a pooling and a normalization step right afterwards. Remember, sentence init transformers automates all this process of tokenizing, passing it through the model, pulling over token embeddings, and normalizing it. Pooling is going to get you that one single vector. Normalization is going to get you that vector that's it's going to make sure that the output vector is of length equal to 1. Here's another one that Calm Embedding Multilingual Mini V1 is a Quinn 2 model. So Quinn is a very popular series of models that are performing very well in the open source community, and at the time of this video, their embedding models, the Quinn 3 embedding models, are the highest ranked embedding models on the leaderboard. And finally, here is the model that we will use. It's a very tiny model. It is based off the BERT model, and it has a pooling and a normalization layer as well. And so you can see they all come from different models, and we're going to do step by step show you how sentence transformers actually produces these embeddings, so that you'll gain more deeper understanding as to what it's actually doing behind the scenes. So first we're going to talk about tokenization. So these are the different types of tokenization methods. We're not going to go in depth on this, but it's just I wanted you to be aware of them so you can research them on your own. We have byte pair encoding and byte level BPE. These are commonly used by OpenAI in their embedding models, and they are very popular. Word piece is the one that's actually used by our embedding model, and then the unigram language model is another one that's used in T5 and other models. All right, so let's make sure that we're loading in this all mini LM L6 V2 model, and we're going to pull out its tokenizer, and we're just going to print out its base vocabulary size. Vocabulary size is how many tokens this model knows about. And so whenever it's trained, how these tokenizers are built is that their tokenizer itself is trained on a corpus of text. And the model learns an optimal set of tokens to be able to represent all of that text. And then for any future pieces of text that you pass through that model, it's going to use those base tokens to tokenize that new piece of text. And so we can see that our mini LM L6 V2 is using a BERT tokenizer. And you can see this is the tokens that it uses for unknown, separation, padding, and class. Usually the class token goes at the front of every single sentence that's passed into the model and can actually be used as a contextual embedding within itself. And so I'm going to tokenize this sentence right here, this very simple sentence saying embedding models are really cool. And we're going to see that the tokenizer itself, when I call tokenize on the sentence, produces this list of tokens. And you can see here that we have these pound signs in front of some of these tokens. It broke up the word embedding into 3 different tokens, 3 subwords. And bed and ding have these 2 pound signs on it. So you can confirm this for yourself, but the word piece tokenization algorithm that I shared above here, word piece, and if you use word piece, what happens is that it distinguishes between bed being by itself or bed being a part of the previous token. So if bed was by itself, like it was just we passed in bed would be by itself and it wouldn't have these double pound signs here. But since bed is a part of the embedding model, the embedding word, these double pound signs essentially say, make sure to attach this token to the previous token. And so you can see how this changes. If I instead just pass in bed, the double pound signs will leave. It'd be just bed. And then obviously the word ding just by itself, there's no pound signs. And so the double pound signs in word piece just mean this is part of another word. Please attach it. If you want to reconstruct a sentence, you have to attach it to its previous token. And the other 4 words were not tokenized into subwords. And so they were just left by themselves. And so the number of tokens that were really needed here were 7. And now we're going to compare that to OpenAI's Text Embedding 3 Large, which is its largest text embedding model. And we're going to see that its vocab size is a whole lot bigger. It is it's over 3 times the size of our mini LM model. And so it has about 100,000 tokens in its vocabulary. And then what I'm going to do is I'm going to encode our sentence and I'm going to decode it to see how it tokenizes a sentence. And as you can see, it doesn't break embedding up into 3 subwords. Like we have embedding. Here it breaks it up into 2 subwords, embed, ding. And the other 4 words are still left by themselves with some spaces. And remember that OpenAI uses byte pair encoding. And so these are all bytes. That's what the B means in front of it. And so we also see, since it didn't break embedding up into 3 subwords, it broke it up into 2, it only used 6 tokens. So now what we're going to do is I'm going to step through, pull everything together, and I'm going to show you how we can actually generate an embedding step by step. So instead of just pulling in the model using sentence transformers, I'm going to pull in the model and the tokenizer using the transformers library. Remember I told you that sentence transformers is built on top of transformers, and this is mostly how it does things under the hood. So we have the tokenizer and the model here. What I'm going to do is I'm going to tokenize our sentence that we're using above, and I'm going to set all of this here. And what we get is a list of IDs and an attention mask. An attention mask tells the transformer model which tokens to pay attention to whenever it's passing it through passing it through. And so if a particular token has a 0 instead of a 1, see all these have 1s, if it has a 0, the model will essentially ignore that token. But we want to, in this case, the intention mask is saying it's all 1s. It wants it to pay attention to every single token in this list. And if we convert this to tokens, we'll see that we get the same tokenization here that we got above, right? Whenever we just use the tokenizer from sentence transformers, we got embedding models are really cool. And here we got embedding models are really cool, except now we have this class token at the front, which is an industry standard to put it there, and it can be used and is used quite often as a contextual embedding whenever that embedding for that token is produced for the entire sentence, and then a separation token at the end. And this is pretty industry standard to put those class at the front, the step token at the end, and then have the tokenization in the middle. So what I'm going to do now is I'm then going to take these tokens that were produced by this whole entire output here, and I'm going to pass them into the model, and I'm going to pull out the model's last hidden state. And so the last hidden state is the last step of the model, and it outputs an embedding for every single token in this list. And so we should have 9 embeddings, considering that we have a class and a sep token plus the original 7 here. And it passes all these embeddings out. It passes all these token embeddings out. It's the last step that it does before it eventually converts that to probabilities, because the output of transformers are probabilities. But here we're just going to get the token embeddings because we just want to build a single embedding for the entire sentence. And so as you can see here, this output of the model is a tensor that you can forget the 1. It is just a 9 by 384 dimension matrix. And so that's 9 384 dimensional vectors for each of the 9 tokens that were here. And then this is a pooling function that all it does is just average over all the embeddings. It's very simple. And then what this is going to do is just produce one single embedding. That's an average of all of them. As you can see, it's a 1 by 384 dimensional vector. And then finally, we did the tokenization step, we did the pooling step, now we're going to do the normalization step. And we can do that using, right here from PyTorch, it has this functional library here, and we're going to call the normalize method on that sentence embedding we produced out of the pooling method. And as you can see, we get a single embedding. And that's pretty much what sentence transformers is doing under the hood. It's going to tokenize, pass it through the model, do a pooling operation over the contextualized token embeddings, and then do a normalization step to make sure the embeddings are length equal to 1.